Okay. So hello, good afternoon, everyone. So today we'll be seeing, yeah, let me just share the screen and we can start the presentation. So yeah, today we will be seeing about, we'll be talking about time series model, our model. So before that, maybe I missed some. So like you guys are introduced for new challenge or for week 11 challenge today, and you have, I guess you've seen how to work with Y Finance and another type of libraries and also time series models. Have you seen about time series model before this? Maybe can confirm me to this question, like with thumbs up or something. Have we seen about time series models and other kind of time series related models and concepts before this? Anyone who might remember? Some right, okay. Some right. Maybe can you write it down? So like, have we seen about the model specifically, or how we've just compared? Like, what is the concept, or how we implemented it? We had a data that is dependent on time series, I believe. So maybe if you can just write me on the call message. So yeah. Meanwhile, we can continue. Thank you, Samri. Okay, so what is time series model? So if we were doing or working on time series models on different type of time series models before, then this is not going to be in class. So time series model is it's a statistical or machine learning approach. It's used to analyze and predict data points collected over time. So these models account for temporal dependencies and patterns such as trend, seasonalities, and cyclic behavior. So when we say when we say that it is a model, so obviously we're talking about or we're saying that it's a model or it's some kind of machine learning model that it's used to predict something. Normally, why do we have a time series dependent model? It's because um, we have a specific data that needs that type of treatment, right? So while we have the data points that are collected over time, then we use the time series model in order to predict the output. So these models account for temporal dependencies and patterns such as trend, seasonality, and cyclic behavior that we've seen. So we've seen that while we were talking about time series data, we've seen that there are trends and seasonality and cyclic behaviors. We can notice those type of behavior on time dependent data, right? So trend means like we might see some type of increment or decrement in the data that is specified in some range, in a specific time range. That is called trends. Seasonality, maybe some behaviors will keep showing up uh, waiting for specific time. So that is called seasonality. So that or they have a season to increase or decrease or to show some characteristics. And also cyclic, it's more of related with the two concepts. So we have seen this three type, I guess, not only three, also noise, right? We have added also the noise character of the time series data. And also, yeah, we have seen this type of characteristics of a data. In order to treat or in order to take a measurement on those type of data, we use the time series model. So um, in reference to this week's challenge, so this challenge states that predicting exact stock price using all historical data is exceptionally difficult, aligning with the efficient market hypothesis. So therefore, our models are used to forecast volatility, identify momentum factors, or serve as one of many inputs into a large decision-making framework rather than for direct standalone price prediction. So the aim is instead of just predicting data, this type of data directly, we'll try to compare them or we'll try to see if there's another factor that will influence the prediction or that we feel like it will influence the last result. So we're going to see the classical statistical approach and the deep learning approach, which is the LST, and the other one, the classical statistical approach, are the ARIMA in the SARIMA models. So ARIMA and SARIMA models are the mostly used type of time series modeling. So what is that? What are they? So ARIMA is a powerful and maybe if there's something written on the commentation based on the question that I have asked before. Let me check. There is none. So maybe I wanted to ask if you guys have you guys used like ARIMA or something or modeling on the when we were seeing on time series models before. Maybe if there's anyone who can remember this, yeah, write me. That would be just useful to know. So let's start with ARIMA, which is autoregressive integrated moving average. So it's ARIMA is just an abbreviation for this sentence. So it's a powerful and widely used statistical method for time series forecasting. It's a linear model that captures dependencies between observations in time series. So the ARIMA acronym stands for its three core components that is related with what they are doing. So let's start with the AR part, which is autoregressive, and the parameter that will describe or that will show this part is the P. So what do we mean by autoregression or autoregressive? So let's say component. This component indicates that the current value of the time series is a linear combination of its own past values. So think of it as predicting today's stock price based on yesterday's, the day before, and so on. So the P parameter denotes the number of lagged observation to include in the model. So the point is, so we're talking about time series data, right? So what is the we need to have a specific characters that will identify time series models and other machine learning models, right? Models. So the specific one of the main thing is so since time series data, we are seeing the difference of the difference implication or generation depending on the time. We need to have some relation between the data, the happenings or the observations that we have for today and yesterday and that we're going to have tomorrow. So because we feel like the previous data are going to have a specific influence on the next data. So the parameter P will indicate that. So it says the current value of the time series. It's a linear combination of its own past value. So like think of it as predicting today's stock price based on yesterday. So like if someone had like maybe forget about the stock value. So if someone had said had told you yesterday the taxi transportation fee from I mean Magananya to Hayat was like 30 bir, then you can just say that okay, then it's 30 bir, okay, because it's yesterday was 30, so today probably it is 30. If it is not 30, then it is not going to be 25. At least it is going to be 35 or something. So the previous data or the historical data that we have or the data that we have is going to have an influence on the decision that we're going to make for today and also for the prediction that we are going to make using the model. So this parameter will decide that. So it denotes the number of lagged observation to include in the model. So how many days, how many months, or how many previous value do you need to integrate in order to predict today's data? Okay. The other parameter or the other parameter that will describe the character is I, which is integrated. So this part involves differencing the raw observation to make the time series stationary. So stationary series has constant statistical properties, which is the mean variance autocorrelation over time, which is a crucial prerequisite for ARIMA models. So the D parameter represents the number of time the raw observation are differenced. So there is this one concept. So the data that we're going to have, as we mentioned earlier, it might have different characters, right? It might have trend, it might have seasonality or cyclic, right? So basically it means the data that we're going to have is not stationary. So in order to the models to calculate the prediction or in order for the models to understand the data that we're going to give should be stationary data. So what do we mean by stationary series? So by the statistical language, they need to have a constant mean, variance, and data correlations, right? So they might increase, they might decrease. That's not the point. The data is not static, but it's stationary, or it is increasing or decreasing in a linear manner. So these three characteristics or metrics are going to be constant over time, which is this is a crucial prerequisite in order to use the ARIMA model. Okay. So what is the advantage of the D parameter? If the time series data that we have is not stationary, so the D will just decide how many differentiation do the data should go through in order to bring or in order for the data to become stationary. Okay. So stationary, it's a time series stationary if it's statistical property, as we mentioned, those three statistical properties do not change over time. So non-stationary data often exhibits trends or seasonality, as we have mentioned earlier. So how are we going to identify, rather than calculating these three metrics? We can make a test, or it can pass a statistical test like the augmented decay Fuller or ADF test. So what is the ADF test is what the ADF test is going to do is it's a low, we have this p-value, it is going to calculate the p-value. So if we have a p-value typically less than 0.05, uh, from the ADF test, so we're going to have an information about the data that we have is stationary. So in this case, the value of p is not so the data is not we're not supposed to differentiate the data, so because we already have a stationary data. If it's not, so then we apply differencing the I component until it becomes stationary, so we can start from 1 and increase it, right? So that is what the concept of I or integration in ARIMA model, that is um, the characteristics. And the other one, or the last one, is the MA, which indicates the moving average. So in parameter, the Q will indicate this future, which is, it indicates that the current value, it's a linear combination of past forecast errors. Okay, so we're going to assume wherever we're working with the data, we're going to assume that the previous of data have some errors, right? It's what we call it. Mm, Maybe so we can have a specific plus or minus something, right? So it might be it might like the value might be specific amount, the true value might be specific amount greater than this or specific amount less than this. So uh, the Q, it's going to assume that the current value is a linear combination of the not only the true value of the data, but it also the past forecast error. So it smooths out short-term fluctuations. So the Q parameters denotes the number of lagged forecast errors to include in the model. So if we're going to count the 9 previous days or 9 previous months, this Q value will just smooth the previous 9 months error or 9-day errors. So this is just the moving average. So ARIMA is the collection of these three components, which is how many days are we going to, how many time actually are we going to consider while predicting the future, and like how far do we need to go in order to make the data stationary, and then how to deal with the error that the data might have. So these three parameters will just judge, will just decide are the main characteristics of the ARIMA model. So if you've seen this, when to use ARIMA model. So ARIMA models, they're suitable for time series data that exhibit trends but do not have a strong consistent seasonal patterns. So they are relatively simple to understand and interpret, making them a good starting point for many forecasting tasks. So obviously it's time series data, like it's the first model that will the first famous and easily applied model while coming to the time series data. So if the data is obviously time series, and if it exhibits trends but not have a strong consistent seasonal patterns, then we can apply the ARIMA data. So for time series data that have a trend behavior or character, ARIMA models are going to be the preferred models. Okay. Sorry, let me check. And then the other time series model is the SARIMA model, which is the seasonal autoregressive integrated moving average. So it's just seasonal ARIMA. So as we have said, or as you can just understand from the name from the beginning, ARIMA is for mostly encouraged for seasonal data. I mean, trained time series data that have the trained characters, while Sarima is for seasonals. So Sarima is an extension of the ARIMA that explicitly handle the time series data with seasonal components. So many financial time series like stock price can exhibit daily, weekly, or monthly seasonal patterns like higher trading volume on certain days of the week. So Sarima adds four seasonal patterns. Again, the P, D, Q, and M. So as you can see, most of them, the P, the D, and Q variables are the same variables that are on in the RMI models. Okay, so P is the seasonal autoregressive, which is the number of seasonal lag observed to include. D is the seasonal integrated, the number of seasonal difference required to make the series stationary. And Q is seasonal moving average, which is the number of seasonal lag forecast errors to include. And then M, which is the seasonal period, it's the number of observation per season, like 5 for weekly seasonality, like how many times are we going to observe this data, or uh, if it is a stock value, like I mean a stock data that is going to be released daily, then for weekly, if you have a weekly data, so there is 5 observation. Okay, so if it is a monthly data, uh, 12 for monthly seasonality and monthly data. So like if it is for a year, and if it is a monthly data, we're going to have an observation or in body of tool. So this is just a unique feature Sarima have, because since it's as we have said, the difference is that uh, it have the Sarima specifically have or handle Sarima, I mean seasonal data rather than that is what makes it different from the Arima model. So like this numbers or the value of M or the seasonal period will just show us in how many seasons is the observation observed or the seasonality observed. So when do we use Sarima? Obviously, when our time series data clearly shows recurring patterns at fixed intervals, like daily stock price patterns over a week or monthly patterns over a year. So Sarima is, since it has the seasonality characteristics, it's somehow complex than Arima, but for seasonal data, it will provide significantly better forecast. The other is the deep learning approach, which is the LST. Uh, okay, so long short-term memories. We worked with LSTM state, the LSTM model before. So the difference is previously or before the LSTM, before applying LSTM for time series data or before just introducing LSTM model, we usually the type of deep learning models that is used for time series data is the recurrent neural network. So RNA it was specifically designed to handle sequential data and overcome the vanishing gradient problem. So the vanishing gradient problem is like on deep neural networks or on neural networks while working on neural networks while moving from layer to layer. We're calculating weights. So after moving from one layer to layer, we'll just calculate if that weight should be is the right weight for that or not, or what should be the next weight in order to move the next layer in neural networks. Okay, so the vanishing gradient problem might happen. So like if the so just we can move from layer to layer by multiplying the weight the previous weight by some numerical value which is between 0 and 1. So while those values became minimum, while we're decreasing those values or the weight, while decreasing the numbers that we're going to multiply the weight with, the original number, which is the weight itself, will be minimized. So if the weight of a neural network or a layer is diminished, then it means we have literally no significance on the weight. We're not changing the weight. While moving from layer to layer, we're moving with the same amount of layer. So that problem is called the vanishing gradient problem. So that was the problem that we like people will face on while using RNA for time series data. So the traditional RNA face when dealing with long-term dependencies are like ARIMA, SARIMA, which are linear statistical models. LSTM are non-linear deep learning models. So conceptually, it have a unique architecture with gates, input gates, for gates, and output gates. So how are they going to work? This allows the LSTM, which is the long short-term memory. As you can understand from the data, I mean from the name, it have It have a long memory and long-term memory and short-term memory. So it's specifically designed to handle sequential data and overcome handling the vanishing gradient problem that traditional array names face with when dealing with the long-term dependencies. Unlike ARIMA and SARIMA, which are linear statistical models, LSTM are non-linear deep learning models. So deep learning models are not they don't specifically need the data to be linear, right? So uh, or statistical. So if we're using a listing, we don't need to bring the data to a to a stationary format or to a stationary character. So a listing is going to be helpful to use those type of data or to predict those type of data. So LSTMs, as we have said, that there are the input gates, the forget gates, and the output gates that control the flow of information into and out of the cells. So this allows the LSTM to selectively remember or forget information over long sequence, making them highly effective at capturing complex nonlinear relationships and long-term dependencies in time series data. So it's particularly useful in financial data, where events from the distant past might still influence the current trend. So what we've mentioned on ARIMA and SARIMA model is that there is a specific time range that we're going to use. So if the data is out of like for the p-value, if the data is if we have like if we say it's 9, so the current data that we're going to predict will be dependent on the previous 9 data, right? But for long short term memory or for LSTM, we don't have that type of specification. So there might be time range, maybe financial data or some type of data might be dependent on literally very like before on the price that were before a year or before 2 years or something. So in that type of scenario, LSTM will be able to handle those type of data or the influence of those data or the current prediction. So they have this, they can understand or like we understand the concept of weight, right, on neural network. So LSTM will just have more weight or more they will give more chance for the data that they feel like it's more important, not only based on the time range, based on the significance of the data. So that is the difference between LSTM and the other data. So instead of capturing just a specific amount of time range, they can just specifically load um, far away data, so they might give it a better weight. So if the models if the model understands that this specific data will have more impact on the prediction, even if it's a data that is occurred before, that had occurred long time before. So for the data preparation for real estate models, like most neural networks, normalization or scaling, which is they they will perform the best when input data is scaled to a smaller range, like it's between 0 and 1, using techniques like minimax scaling. And there is the sequence equation, which is time series data needs to be transformed into sequence. So all the data that we're going to use for time series models are dependent on the time series data, right? So here they are specifically need to be transformed into sequence. So using the past n days of data to predict the next n days. So this involves creating input-output pairs where the input is a sequence of past behaviors and the output is the values that is going to be predicted. So the architecture and hyperparameters, they will require more architectural decisions and maybe hyperparameter tuning compared to ARIMA and SARIMA because they are deep neural network models. There are some specific characters that we, like hyperparameter tuning that we apply on neural networks, for example, so they need that. So this includes choosing the number of LSTM layers, the number of neurons in each layer, the activation function, the optimizer, the loss function, and training parameters like epochs and batch size. So we need this type of specific judgments or decision in order to work with the LST models. So specifically, when are we going to use LST models? They are ideal for literally complex data and large data, okay, and nonlinear data that are not going to be that are not going to become stationary data easily. And the traditional statistical models like the ARIMA and SARIMA cannot handle those type of models. So specifically, we use LSTM for these conditions. So the purpose is LSTM can selectively remember or forget information over long sequence, making them highly effective at capturing complex nonlinear relationships and long-term dependencies in time series data, as we have mentioned earlier. So this is particularly useful in financial data, where events from the distant past, as we have mentioned, are going to be important. So, yeah, one disadvantage while using the LSTM models are they need a highly intensive or larger amount of data. So they benefit from more data since any type of neural network data model they are used or they got an advantage from a large amount of data. They need a large amount of data. So they are obviously computationally expensive, but they are more computational intensive and less interpretable. So while coming to Arima and Sarima, they can be interpreted like using model interpreters. While coming to the neural networks or yeah neural network models, we cannot. It's like a black box. We cannot understand how this type of decision or prediction we achieved based on the previous data. So that is going to be the disadvantage. So yeah, I guess. So do you have any question on the concept? On the things that we have? Any question? Do you understand the concept of time series data? I would really appreciate some participation here. Okay. So the point is like the second part is the data preparation in the architecture. So specifically when to use the LSA model, they are ideal for time series data with complex nonlinear patterns that traditional statistical models might struggle to capture. So this will directly emerge from the disadvantage of ARIMA and SARIMA. So while we were talking about ARIMA and SARIMA model, what we have said is we need to make a test so to understand whether the data is stationary or not. So if the data is not stationary, which is the mean and other factors are not going to be constant, then we will try to make the data constant, right? So we have mentioned this while talking about the ARIMA and the SARIMA model. So, but there are some data that are literally complex and they're not linear, okay? If they're not linear and it is going to be difficult to bring those data to stationary. So bringing them even if it is going to be possible, bringing those data to a stationary character is going to make the data to lose their characteristics or their what they are trying to tell about that specific scenario. So the ARIMA model is the enlisting model, they can understand that complexity without the need of bringing the data to stationary to be stationary. We can just use those type of complex data in order to predict the future. So um, they are particularly powerful when you have large amount of data. So this is directly related with deep learning. Any type of deep learning models, they need large amount of data, and they perform under the availability of more data. So yeah, specifically, if the data that we're going to time series data is more complex, so we will prefer to use LSTM or the deep neural network method to predict the future. Is that clear, Sunlight? Okay, thank you. Um, any other question? Okay, if not, I'm literally facing the error while using while yeah a package complete. So but let's see. So something that I guess it's specific here. Something that I actually something that you guys might face because I have faced that as a conflict. I mean package conflict. So um, I will literally update this code and like before uploading it. So be careful about the package. We need to be careful about the package specifically that NumPy will cause an error, like a major error. So we will. I will just while uploading this demo, I will update this. The NumPy will just have a direct effect on the PMD ARIMA. So this is specifically the library that is going to help us to get the ARIMA model. So but those are going to bring the package conflict. So yeah. So let's starting from fetching the data. We have used Y Finance in order to using the ticker name Tesla for data to get the data from the start date and to this in date. I We have downloaded the data using Y Finance. So number of data points 2,535, and this is the data that was going to use. So this is not going to make the like literally the ARIMA test because yeah it just failed. But at least we can see the first concept, which is we need to see whether the data that we're going to have is stationary or not. So I have mentioned the augmented decay So this test is going to help us whether to decide whether this data is stationary or not. Okay. So here we have divided the data to train size and train data. So ADF results, it's AD for using AD Fuller test for the train data. So if the AD results is greater than 0.05, which is the we call it like the P, maybe you can call it the P value. So if there is greater than 0.05, it says the series the time series data is not stationary. So here we need to apply some differencing. But if it is not, then it's okay. So here we've got the ADF statistics like negative 1.0955, and the p-value is basically 0.71. So as you can see, it's the series is not stationary because it's greater than 0.05 value. So in this type of case, you will decide to apply while using the ARIMA model to apply the differencing or the value d that we've mentioned. This is the one of the packets that is causing the error. So, but this is going to be the logic. Okay. So there are, if we're going to use for the ARIMA model prediction, if we're going to use auto ARIMA, then you can just let the ARIMA model to decide whether to decide to determine the d value. So if you're going to if they're going to do if the data is stationary, so there's no need of there's no need to use the d value or the differential value. But if it is not, we can ignore value one, just the model itself will decide for the d value. Okay, so here we have the ARIMA model. We are using the auto ARIMA, and then the forecast result will be also ARIMA models to predict the N pairs, which is N pairs is equal to N forecast, length of the test data. So here we have the length or the number of test data, not the data itself, but the number of test data. So here we can just use based on the seasonality that we can gain. We're not just applying for the ARIMA, but if the model have or if the data have some specific seasonality, we will decide with the ARIMA model giving it a state, giving it a stationary or I mean a seasonal value. Okay, so we've made a seasonal value true here. So if there is seasonal, then the seasonal data or the seasonal data or number will be applied. So it really does it work. So by sharing this data by this code, I will just update the code itself. But for now, just Now we're having or we're implementing what we need to implement if we decide to go with the ARIMA or the SARIMA model is the auto ARIMA. So the auto ARIMA will decide whether the data has seasonality or so to go with the SARIMA or whether the data has just a trait to go with the ARIMA model. And then the D values and other specific values can be decided by the P value and the Q value, which is what the amount of you can just give the amount of previous values that it needs to look, and the amount of the p-value, the differentiator, and m is cos to 5. So if it is going to use the seasonal data, weekly, you could just decide what its weekly seasonality. For daily data, it's 5 business days. So the Alfarima model will decide what amount of the seasonality to take. The P1 and the starting value for P making it 1 and the maximum value making it 5 will just say that so minimum you're going to look for the previous 1 day data. So if it is a daily data, so we'll fetch the daily data. So that is going to look the previous day data in order to decide the next day. For example, if we're like today it's August 6th, so if we're predicting August 7th, so just it is going to take the August 6th price market in order to predict for the August 7th. And if it is for August 8th, then it is going to take the August 8th prediction. So this is going to be the pattern. So yeah, just putting or the figure, understanding it, putting those values here, we can just decide what type of prediction we're going to have, and the model can iterate with the data. I will share this notebook after figuring out like the right type of antibodies and packets that are going to be used for this. Okay, so any question, or do you understand the concept and like how to apply how to use the models? Anyone? Anyone? Okay. So yeah, maybe like after seeing the data and after understanding the listing method, is there anyone who would love to go with the listing modeling? Okay, and then in this case, maybe we can end the session here, I guess. Okay, maybe. Yeah, we can end the session here. So just if you understand the concept and if you understand the last part, and you know how to say that after understanding your data, how to say this values, the p values, the q values, the starting the d values. So like giving just the model or the auto ARIMA. If you decide to go with the ARIMA or the SARIMA models, giving it the range in which the data can iterate through, or like all the 3 values or all the four values if there is going to be a SARIMA, because we're just providing the model a choice whether to decide with the SARIMA or with the ARIMA part. We're giving the chance for the model to decide, right? So giving you the right parameters for the decision will just help you to get the final good result. Okay. So maybe do you have a question or do you grab the concept? Anything? Okay, in that case, we can end the session here. Thank you everyone for being here. Good luck with your tasks.